Hello, mic test, sound check. Thanks to Doc Mon for that very cool introduction. So just a special shout out to Doc Mon. He's one of my mentors when I started way back 2017, and definitely if he's not the one who guided me, I'm not here today. Yee? Sige na.
Pakita yung dimples, pare.
Di ba, hindi ako makafocus eh.
Kung single ka daw or ready to mingle, sabi ko sa table doon.
Ay, sorry. Sorry talaga.
Kalma ko, Ariz!
Okay, guys. Thanks everyone for, well, no choice, attending my talk today. And I'm going to talk about understanding and recreating process injection techniques through Nimjector. So, first of all, I'd like to introduce myself. My name is Ariz Soriano. I'm also known as Arizi. I'm not sure if you've seen my handles throughout some CTFs online or some blog posts or just random tweets about information security. Currently working as or leading the team of Red Team Operations at Theos Cyber Solutions, and I've also worked as a blue teamer before transitioning as a red teamer. I've also been a certs collector. As Docmon mentioned, I've got a lot of certs, mainly focused on red teaming, which is why I'm red teamer now. And I'm also focusing now on red team research and malware development, which is why I did this tool. So first, let's set some expectations. You won't learn any new fancy tools or techniques today. If you're gonna use the tool that I'm gonna present, please use it at your own risk. Don't use it on, you know. And lastly, our main purpose for today is to learn process injection. So let's run through the agenda for today. Let's run with process injection primer. Let's revisit some techniques that are well known. Let's go through some API calls since it's the most significant part of doing malware development. Lastly, it's the tool. So now, let's start with some information about process injection. So process injection is a method of executing an arbitrary code in the address space of a separate process. So basically, it's a way to execute a shell code. As everyone knows, shell code gives you a callback if, well, default or basically people use the shell codes for a callback in their C2s. So an example here in the image is interpreter shell code. And process injection is usually used to execute under the context of a legitimate process. So if blue teamer sees a process injection or a callback happening from an explorer.exe versus an a.exe or a random.exe, if they Google it, you wouldn't see any indicators that it's malicious. So it's basically a part of deception techniques. So now let's run through some basic structuring of process injection. So process injection typically has three main parts. It's the allocate, write, and execute. So let's use my very well designed diagram. So first, an example of a call is virtual alloc_x. Virtual alloc_x allocates a writable memory space in another process. Next, it's the write. So an example would be write process memory API call, which writes a shell code in another memory space. And lastly, it's the execute. So once you've written the shell code, you only need to do is to execute it using a create remote thread. So now, let's revisit some techniques that are very well known. First, it's this one is a resource from iRed team. If you want to learn about process injection techniques, you may check this out since this site got a lot of examples. So let's run through three techniques for now since there are a lot of techniques and it's very gruesome for morning guys if you learn process injection throughout the day. So let's run through this create remote thread. So create remote thread is one of the oldest techniques that are well known. It's easily detectable, of course, since it's already old, and but still it builds your foundations for process injection. Since it's the example that I gave a while ago, and it gives the structure for everyone to learn and how to see the different parts of a code when it comes to process injection. So for this one, let's run through some API calls. So open process. Open process allows you to open a target process wherein you want to inject a shellcode. So for this one, let's run through this by opening the target process, explore the exe. Now, let's allocate using virtual alloc x. So it stores on this code snippet, it stores the memory address on the RPTR variable, which will be used on the succeeding code snippets. Next, it's the write process memory. It writes the shellcode on the allocated memory. And lastly, it's to execute the shellcode using create remote thread. Now, this is one of the more advanced ones. Let's run through process hollowing. So process hollowing is a technique wherein the remote process is being hollowed so that you can write a shellcode on that hollowed or unmapped process. So first, what it does is it creates a process in a suspended state so that once it's paused, you can tweak it and resume it so that once you have modified it and the shellcode has been written, you can execute it by resuming it. So first, an API call is create process. So you will create your own process on this one by creating a suspended process. You can, once it's paused, you can modify the contents of the process. Next, it's ZW query information process and read process memory. So what it does is it computes the address block of the section and the remote process of the address block of the process that you want to be unmapped. And after that, once you got the address of that the address block, then you can write the shellcode in that section. Lastly, it's a resume thread. Since you have suspended the process, once you resume it, the shellcode will execute. Next, it's early bird APC queue. Somehow it's similar to process hollowing since it starts with the suspended process, but still the methodology or the setup where you put the shellcode is a bit different. So first,
Of course, we're gonna do everyone right. Na-miss nyo kanina na si Sir Archie, hindi din siya uminom, di ba? So, Sir Archie, let's do the honors. You're not getting away. So, if...
Akala ko ba Hall of Famer na ako dito sa ganyan?
Kaya nga, dapat Hall of Famer, set an example. Hall of Famer always set example. Naps, doon ka. Sabi mo.
Ubusin mo yan. Yan, oh. Santongga yan, santongga.
The voodoo, what you don't dare do, people.
Nagkapi-api ko makano ng blue level.
Ay, ito, inutusan akong bunda ko.
okay, thanks boss. Okay, so now going back. Tangin ang hirap magsalita. Let's go. Okay, going back, let's run through early bird APC queue. So, early bird, it's given the name early bird since you're abusing the, di ko in-expect to. Wala sa practice ko to. Okay, so it's given early bird since you're abusing the queue of the APC queue before it eventually starts. So basically, what it does is it's similar to process injection, wherein you suspend the process first, and then you allocate a new space in the remote process, wherein you write your shellcode and you eventually point the address of the shellcode in the APC routine. May piyok tuloy ako. And then eventually, once the APC is queued on the main thread, once you resume the process, the shellcode executes. So let's run through again some API calls to make you overwhelmed with my presentation. So first, it's the create process. So what you do is you create a new process in the suspended state. Next is you allocate again and again. Allocate a memory space in that remote process in Explorer.exe. Next is the write process memory. You write again the shellcode in that allocated memory space. Next, it's the queue user APC. So this is one that I mentioned before. You point the address of the shellcode in the APC routine. So once you start the process or resume the process, it's the first one that gets executed. Lastly is the resume thread. So it's just resuming the process so that the shellcode will get executed. So what's my point of why I presented those techniques? So the structure exists on all techniques. So as you have heard, I've been mentioning you allocate on remote process, you write on that allocated memory space, and you execute that shellcode. Next, I've shown the code snippets just to show that coding different techniques, it's quite gruesome. It's quite hard to structure every different API calls just to make a working process injection binary. And lastly, it's very important to understand the Windows API call since it's the bare bone of malware development. So now, let's run through some information about Windows API calls. Windows API calls, it utilizes existing functions from a DLL to execute process injection. There are different ways to call and execute API calls. It's via kernel 32 calls from kernel 32 DLL or NT-DLL calls. And there are additional ways to execute via system calls, via syscalls and get syscall stub. So let's run first with the kernel 32. So as mentioned, you're just gonna play with the functions residing in kernel 32 DLL. So most of the functions here are being used by legitimate processes. So by utilizing the API calls on this DLL, you somehow evade some detection techniques. Next is you can use the documentation of Microsoft since I think pretty all of the API calls that are being used in kernel 32 are well documented in Microsoft. So just fire it up and you're ready to go. Next, it's the NT-DLL, so it's the native API of Windows. You're calling functions residing in NT-DLL, and the problem here is they are undocumented functions. So as you can see in my image, once you try to Google dork NT write virtual memory on Microsoft Docs, you see nothing. But there are good Samaritans that are creating documentations for NT API, so you can try to use these resources. And there are a lot of other resources, but you can still prioritize using these ones. Next, it's the system calls. So somehow it's just similar to the NT API since NT-DLL is just a port to access system calls. So for the system calls, it's if you're gonna use this one, the structure of syscalls are just similar to the NT functions. It's just invoking in anti-API functions without directly calling functions from NTDLL. But the caveat here is the syscall is strictly, it varies from different Windows versions. So for this one, just to give an example, there are two repositories that are well used for malware development related to system calls. It's the syswhispers and Nimline whispers. So for the syswhispers, it generates an assembly file that can be imported to make direct system calls. And next, it's Nimline whispers. It's just ported for Nim. Next, it's the get syscall stub. So syscall stub is just same concept with the syscalls, but you don't hard code the system calls. For this previous example on the image above or below, as you can see, the assembly code is hard coded on the function, but on the get syscall stub, you dynamically resolve every anti-API function so that you won't handle the problem of hard-coded syscalls on different Windows versions. So the main resource here is nim get syscall stub. So a sample image on the right side gives you an idea on how it works. It checks dynamically the address of anti-open process, anti-write virtual memory, anti-create threadx, and eventually it executes the shellcode. So, are you still okay, guys? Overwhelmed? I'm okay, I'm okay. So now, Maya. So now, it's kind of overwhelming to learn process injection through that. With that slides, I am not quite sure if I myself would learn a lot. So now, why I'm here today is I'm going to present the tool that I created, which is Nimjector. It's a process injection framework that focuses on learning and, of course, creating, compiling your own payloads, and as well as detecting it. So, a quick image of the GitHub repository. I was able to publish it yesterday in public since it's just in a private one beforehand. So Nimjector is a process injection framework written in Nim. It's inspired by Nim GitHub repositories such as Offensive Nim, NimHollow, and NimCrypt2. So I got this idea of building this tool since I've been using NimHollow. NimHollow is a tool that focuses on process hollowing. So it just automates the compilation of process hollowing written in Nim. And during my red team engagements, I had these experiences wherein the NimHollow binary gets flagged by CrowdStrike, by Sentinel-1, with some EDRs online, and just or anti-scan that the website wherein you can upload the binary, it gets flagged. So I tried to tweak the binary so that it works, and eventually I got tired. Why do I modify all the source codes of the other guys if I can do it on my own? So I just did this tool so that I won't rely on the other guys and just rely on myself doing this process injection techniques. And of course, if I do it myself, I can customize it the way I like it. So one of the goals of Nimjector is it eases the payload creation of different process injection techniques. So as a red teamer, it's kind of hard to think about the payload that you're going to use for initial access. So most of the time when I do some red team engagements, my initial access payload, of course, is not a binary, since it's quite stupid if you attach a binary or a binary in a zip in an attachment, since most of the time it gets flagged by email security gateway. So what I do is I typically chain into stages. So as mentioned in my talk yesterday, if anyone here attended my talk, it's quite good if you do a staged payload. So I just pass the binaries that I do, and typically it's on the stage 2 or stage 3 of my payload chain. So it's quite hard to think of different payload chains just to account the EDRs based on my reconnaissance if I knew the EDR existing in the organization. So based on that experience, I just thought about it, and if I can automate somehow the different techniques that I play with on my day-to-day job, then it makes my work easier, and I won't dwell a lot on my work. I can just sleep and declare I did 8 hours of work instead of just, but instead I just did 3 hours. So with that, I use this tool to ease my payload creation. Next, one of the highlights of Nimjector is a template-based and a modular framework, which I will be discussing moving forward. And lastly, and the most important part of this tool is it highlights the learning while using the tool. So the tools that I've mentioned, NimHolo and NimCrypt2, NimHolo, as mentioned, it's using process hollowing for process injection. In NimCrypt2, it uses early bird APCQ, which is the techniques that I have mentioned. But it's quite hard to learn the process injection techniques by just compiling it. If you're a guy who just downloads a tool on GitHub and just runs it, it doesn't make sense if you just run the tool as a red teamer. You need to, of course, learn the tool itself before running it so that you know how it works, and eventually if your client or your target asks you about the binaries that you have used, you have something to answer. It's quite stupid if they ask you, oh, what binary did you use? What techniques did you use? How were you able to bypass the AV or EDR? And you can't answer it. So this tool somehow utilizes the compilation stage and the learning stage combined. And lastly, it's most of the tools that I've mentioned only focuses on the offensive end, but I've also counted, since it's a modular framework, you can utilize it on the blue team as well. So first, why NIM? Why did I choose NIM? Why it's Nimjector? It's not Nimjector if it's not NIM, so I just forced myself using NIM. But kidding aside, it's just because I'm a Python kid. I've been coding Python since 2013, so I'm very lenient to high-level programming languages. It's quite hard. Well, I can do some C or C++ or even assembly, but well, it bores me though. I just want to use high-level programming languages that has the capabilities of a low-level programming language. So for this one, an example on the left side is just a Python function, and sorry guys, and for the right side, it's NIM. Somehow it looks the same for me, and yeah, it's one of the reasons. It's the syntax that makes it easy for me to code in NIM. Next, it's the compilation. So using NIM, you can easily compile your source code that works on all operating systems. It has a cross-compilation capability for Windows, Linux, and OS X. So in the images above, it does not have an axis, so it's a Linux binary. And on the lower end, it's a Windows binary. So given on the example, it was compiled on the Kali Linux, but I was still able to build a binary that works on Windows. Next, one of the reasons why I chose NIM, it's due to the fact that there are a lot of public repositories for NIM offensive tooling. So it's quite hard to learn NIM and account the fact that you're going to create a malware out of it. So based on that, there are a lot of tools that are very helpful for malware development with NIM. So first, it's the WinNIM. WinNIM, it's a repository wherein it ports all the not all, but most of the API calls in kernel 32, which allows you to create a malware in NIM by just mimicking how to code it in C or C++. Next, it's Nimline Whispers. So Nimline Whispers is very important for me since it's being used for syscalls. As I've mentioned before, the syscalls techniques. I'll deal with that later on. Next, it's the same. It's nim get syscall stub. And lastly, it's offensive nim. Offensive nim is a repository containing a lot of different ways on how to utilize nim for offensive security. Now, let's talk about why nim is being called as a framework. So it's a modular framework wherein it utilizes YAML as its configuration files. So for these examples, the left one is the techniques model wherein it contains all the API calls based on the technique. So as I've mentioned during the first few parts of my talk, I've talked about create remote thread and the API calls that are being used. So using Nimjector, you can define the API calls used for that technique and it will build it for you. So if you can see here, it's defined in the create remote thread, the open process, virtual alloc x, write process memory, create remote thread, and close handle. So these are some of the functions that I've discussed way back, and you just need to define it in this YAML file. Next, it's the kernel 32 to NT conversion YAML file. So it's also a YAML file that defines the conversion of kernel 32 calls versus NT API calls. So I'll deal with that moving later on. Next, it's the API calls for source code is written in NIM as well, of course. So as you can see in the images, each API call are divided per NIM source code. So virtual alloc is written in virtualalloc.nim. Create remote thread is written in create remote thread.nim. And wait for single object is written in wait for single object.nim. So with that idea, if you have defined the API call and the models, you can just look up with the function, with the API call function, and just adding .nim extension to it. With that, you can look up with the contents that you need so that you can build the tool. So next, it's the reusability of definitions. It's not a modular framework if you can't reuse the definitions that you did. So the defined API calls that I've provided can be used for compiling the process injection technique as well as detecting it. So I deal with the detection techniques later on. So,
Sorry for the interruption, Ariz. We just have to announce yung training ni Jigglypuff kasi 10:15. Sorry, Ariz. Jigglypuff.
Alright, so guys, announcement lang. So we'll be going ahead with the web PT 10. Kaya pala ako yung pina-announce, mabihirang po. Good morning. All right, guys. So again, web PT 101 on Kamiya Hall. We'll start in 15 minutes.
Thank you, Sir Jiggly.
Okay guys, going back. Dragon na ako. Okay, going back, the reusability of definitions. So as mentioned, I'll show moving forward how can we leverage this defined API calls on the detection and creation of the payload. So the premise of this is that if you know what API calls are being used in that technique, might as well you can detect it. Next, it's the defined kernel 32 API calls can be easily translated into its anti-API counterpart. So if you can define it, you can somehow use it on the compilation stage, wherein if you want to change the kernel 32 calls into an anti-API calls, then you can translate the complete technique into it. And as well as during the detection, so if you're trying to detect create remote thread and they're using kernel 32 calls, you can try to convert, or anti-API calls, you can try to convert your, the detection works by running every kernel 32 API call and as well as translating every kernel 32 call into an anti-API call so that you can account every call given if there are a lot of variations to it. So as mentioned, there are API call code snippets, so you can just use the API call for each NIM source code. So you can just look up on the functions directory. It contains this API call.nim file, and it contains the source code for that API call code snippet. Next is this modular framework also solves the problem if the API call that you are going to reuse does have different custom arguments. So not every API call has the same arguments. So if you have the same technique with the same different technique with the same API call and it has a different argument, this tool can accommodate it. You can define this outlier API call on this technique and change the arguments of it so that the technique works. Next, as I have mentioned, and one of the highlights of the tool, you can learn while using the tool itself. So it introduces the learning while compiling and detecting process injection. So it's not similar to the tools that I've mentioned that only gives you the binary, but of course gives you an idea on how every API call is being used and what API calls are being utilized to do the process injection technique. So every information of API call are being printed so that while you compile, or if you just want to learn the technique, then you can utilize the tool and learn the process injection technique itself. So given the example here of vanilla technique, it prints every API call. So it's using virtual alloc, RTL copy memory, create thread, and wait for a single object. And as you can see, every API call used an information written in yellow gets printed, which gives you an idea how the API call is being utilized on this payload. So an example would be a virtual alloc, wherein a virtual alloc is often used by malware to allocate memory as part of process injection. I've been mentioning virtual alloc X, and allocating memory, and yeah, given this definition, you would learn that every virtual alloc or virtual alloc X gives you a remote or self-hosted process memory wherein you can write your shellcode. Now, let's run through the functionalities of Nimjector. So first, let's run through the red team capabilities of it. So first, of course, it's the payload creation. So there are a lot of different techniques that are being hosted by this tool. I've used a lot of resources on it and compiled it. There are a lot of resources such as process, NimHolo and NimCrypt2, wherein I added in this tool, and credits to them, of course. But as well as there are a lot of techniques that are not written in NIM, but I've also converted it into it so that I can create a lot of techniques that can be utilized by this tool. And right now, on this date, the tool contains 46 different techniques of process injection that can be utilized by anyone who wants to use the tool. So some examples would be, well, the create remote thread, process hollowing in APCQ, suspended thread, etc., and the callback functions. Next is the mix and match of different API call variations. As I've mentioned on the Windows API call section, there are different ways to call API. And not just API, but as well as syscall. So if I know how to call those, then I've also added it in the tool. So I've added a kernel 32 implementation of each technique, NT-API calls, syscalls as well, and get syscall stub. And with that, if you're gonna compute it, it's 46 times 4 different variations, which gives you an almost 200, not sure. It's lower than 200, but it's lower than 200 techniques that you can utilize and learn on how to use process injection. And next is the optional shellcode encryption and DIL patching for evasion. So these techniques are not, well, it's quite old, but it's still useful. But I think I've just added this functionality so that I can show that it's a foundational technique wherein you encrypt your shellcode so that the shellcodes that you use, if just generated from a interpreter or just in your Cobalt Strike C2, most of the time those shellcodes gets flagged since it has a signature that are well known. And if that shellcode is being written in your binary and it's not encrypted, then the binary that you're going to use gets flagged easily. So I've just added these functionalities as an optional one so that the users can learn and somehow utilize this encryption. Now, for the benefits, as I've mentioned, there are a lot of techniques that can be utilized. So given the example here, there are 46 available techniques that you can choose on. And as a red teamer, what I like is I can try a lot of techniques and play with it so that I can try to choose what technique can I utilize, which can bypass some AVs or EDRs. Next is the learning part. So once you compile the binary or you just print it, if you don't want to compile it, then it prints the information for each API call so that the users could learn what does that API call would mean. Next, it's the variations. As I've mentioned, there are 4 variations as of now. And you can, based on the example here, on the upper hand, you can use, by default, it's on kernel 32. So by using a create remote thread technique, you're using open process, virtual alloc X, write process memory, create remote thread, and close handle. But if you're going to utilize the get syscall stub, it uses the get syscall stub source code of get syscall stub repository, and as well as the NT-API calls. So if you can see here, it's quite different from the one above since it uses open process, NT-allocate virtual memory, NT-write virtual memory. You can see that there's a pattern, that there's an NT prepended to it. So it just means that it's an AT-API function. Now it's about the blue team. So not everyone is doing a tool that hosts red team capabilities and blue team capabilities. So the premise of this idea is that I've already coded the part wherein I know what technique or what API calls are being used for that specific technique, why not check it on the blue team end as well? So first of all, the capabilities of this, of course, is not it's not balanced. The red team capabilities somehow is still on the upper hand. So the blue team is still catching up since it's quite hard to code on the both ends. So right now, the functionalities is that mostly it checks on the static end of the analysis. So first, it's just a string-based detection. So not every binary is being packed or being obfuscated. So it's still useful if you want to have a quick check or a quick dirty check if there is a suspicious API calls that are written inside the binary. So it checks all kernel 32 and anti-DLL calls that are hard-coded as strings in the binary. And of course, the caveats here is the string obfuscation. Of course, if the binary has obfuscation and somehow the API calls that are being used are obfuscated, might as well the binary can't detect it. And next, it's the call checks are not sequential for now, since as I've mentioned, there's a sequence for each API call being used in the binary, and if you don't utilize the open, create, allocate memory, write, and execute, somehow it's not that accurate. And given that the false positive accuracy of this tool is for the detection is still high, but I'd still recommend to use this tool just for a quick check if you want to see if there's a process injection technique existing in the binary. Next, it's the syscall detection. Somehow, it's similar to the strings detection, but it's just about the syscalls. So as I've mentioned, the syscall detection, or the syscalls are being used as, by using some assembly code to utilize the syscalls in Windows. And given that if you use that syscall and in the binary, the assembly code gets written as well. So on the right side, as you can see, the hex code of the shell of the syscall is being written. And if you have that signature of that anti-API call on syscall, then might as well you can detect it as a hex code in the binary, which is written on the left side. So for the anti-allocate memory, here is the syscall hex signature of it. So most of the detections here are just signature-based and not dynamically. Next, it's about the detection. The benefit, one of the benefits, of course, is the detection of the API calls for a quick dirty check, and it uses a heuristic scoring based on the API call weight. Not every API call for each technique is equal. Of course, there are some API calls that indicates that the technique is being used because of this API call. So as an example, in the create remote read, if you use open process, virtual alloc X, write process memory on different techniques, you still don't know if it's a process injection about create remote read. But if you see a create remote read, might as well, it's a high chance that the technique being used for process injection, of course, is create remote read. So with that, in this framework, you can add a weight for that API call so that you know that this technique or this API call is more significant than the others for that specific technique. And for this image on the right side, you can see that since I used a binary compiled by my tool and a next, for the benefits of the blue team, it's, as I've mentioned, it's a payload creation framework, so you can utilize the 46 techniques. And as a blue teamer, it's easy for you to just compile it and run it on your AV EDR on a controlled environment. So if you use the tool and the tool, if you use the tool with your own shellcode, with your own source code, if you want to tweak the source code before compilation, then you won't have any worries that the tests that you will do on your environment is malicious or uncontrolled. So as a blue teamers, you want to test your own environment with a controlled setup. If you want control it, then if you just want to check a malware that can be, if it can be detected by your security controls and you don't know the capabilities of it, then you're gonna be messed up if you don't know how it does. But this tool gives you the capability to first learn how the tool works and compile it on your own so that you know how it works, and you will expect if your EDR or AV did not detect it, then you know what part of the tool or the payload was not able to be detected. Since it's quite hard if you just throw a malware, if you know some malware families such as Zeus or TrickBot, and if you just run it on your EDRs, you don't know what API call was not being flagged, what indicator was not being flagged on that malware sample. So if you control that malware sample, you still have the idea of what lacks of that EDR and what can be improved of that EDR, so that you can contact your EDR provider and say that your tool is shit, you can't detect this shit. So you can do something like that if you have the supporting backup of how the tool or that evasion on that binary works. So now I've talked about Nimjector. It's now about development plans. Since I just did the tool itself, first it's about my own personal use. I've been using this tool for red teaming purposes, so that if I have an engagement for red teaming, I can just fire up this tool and yeah, I can compile my binary and use it for engagement. But still, and next, I just use this tool for presentation here in RootCon, since I want to present here in RootCon. And which is why I just did this tool 3 to 4 months ago, from the idea and the customization or coding of the tool itself. So there are still a lot of plans for this tool. So if you guys are also interested in malware development, feel free to approach me and we can work on this tool moving forward. So for development plans, of course, there are a lot of variations of different API calls and the techniques itself. So as I mentioned, there are 46 techniques and there are 4 variations as of now. And if you want to randomize every API call for each variation, so for example, there's a create remote thread and it uses open process, virtual alloc X, write process memory, create remote thread, create thread X, and close handle. If you can try to randomize the variant for each API call, then the computation for each, going back, if you want to randomize each API call, then the tool will present you a kernel 32 call for open process, NT-API, for example, in the virtual alloc X, a syscall for create remote thread, and a get syscall stub for close handle. With that, as you can see, it gives more variation in the technique. It gives a hard time more for the EDR if they have a signature detection or a heuristic one, since the API calls being used are well versed and very variated, which is why it could give a more capability to evade the EDRs. But for now, and with that variation of randomization, it does not, the computation for the variations of the technique does not compute into 46 times 4, but into 46, four permutations of 46. So it will give a lot more different variations of the tool itself. Next is the evasion techniques. So as a red team, if anyone went here to my talk yesterday, evasion is very important. You want dwell in red teaming if you can do evasion. So of course the tool, if you want to get a lot of red teamers who wants to use this tool and contribute to it as well, then you would want to make this tool evade every EDRs that are existing. So as a red team enthusiast, I would want to make this tool in the near future to be able to evade all EDRs. Not declaring it, but hoping that this tool could do it. So next is the weight or heuristic scoring for optimization. So as I've mentioned, there are weights for each API call in the technique, and yeah, there are still not that inaccurate, but for me, it's still, the scoring is still not optimized, so might as well optimize it. And lastly, for the blue team, as I have mentioned, the capabilities of blue team and red team for this tool is not yet equal. So if I would want to make it equal, the dynamic API hooking for blue team capabilities would be the one to solve that problem for me. Since for now, as I've mentioned, most of the detections are just focusing on the static analysis. If you have the capability to do it dynamically, then you would be able to detect every API call for that binary and check if it indicates that it's a process injection technique in a more accurate way. So for the dynamic API hooking, you can utilize this by utilizing the definitions for each technique defined with the API calls, and just use those definitions to know what API calls you will hook in the binary and know if it was called or not. So with that idea, you can somehow intercept every API call and know if it is a process injection technique or not. So I've been talking a lot, so let's run through some demos. No, pass. So I'll just pass my VM for now, just to show you how the tool works. So this will just be quick. Sir Jerwin, Boss Jerwin, hindi ko matanggal yung ano. Ayaw. Ay, wait. Ayan, yan. Okay. Kali Linux hacker. Ayun. Okay, so now, oh shit, I can see this. So now, let's try to run the tool. So first, as I've mentioned, it highlights the usage or learning of the tool. So let's run through first the... Okay, wait a minute, just a minute. I'll just try to change the display. Displays. Okay, let's use a mirrored one so that I can easily talk. Use as mirror. Okay, so now I can talk easily. Okay. So now I'm talking about the tool as learning tool for process injection. So let's try to list all the techniques that are existing. So as you can see, the tool has 4 to 6 techniques with different techniques focusing on process injection. Now, if you want to learn just about this technique and not use it or for compilation, then you can just use the technique. For example, create remote read, or okay, let's just use APCQ. So APC queue and just see all the API calls that are being used for this technique. So you can see that these are the API calls that are being used by the technique and the description about that API call. So with that, you can learn somehow about the technique on what API calls are being used and what does that API call mean. Next, it's about the compilation. So let's run through the red team capabilities of the technique. So if you want to use the red team capabilities, you would want to use this parameters. So if it does not have this brackets, it does mean that it's not optional. So you need to provide a shellcode for this tool and a technique name, since it would not, the tool would not know what technique you want to compile or print if you don't define it. So let's run through this payload. Let's run the red team capability and let's put the shellcode. So I've prepared a payload that's been here, and let's use a technique create. Just to give an idea on how to use a tool efficiently, you can use Nimjector here on the other side, using a split view of the terminal with Terminator. You can list and print all. So you have here on the right side all the techniques, and you can just copy paste it here, and you can just copy paste here the technique that you want to choose, and just for dash P uppercase, it's just print. So you would have here first the learning part wherein it prints, well, it prints the definition for each API call that is being used, and as well as the source code. So if you don't want to compile it, if you're not going to use a binary, and if you just want to learn NIM and how to call API functions on API functions for malware development, then you can use this functionality. So you can see here that the create process is being called the virtual alloc X, the write process memory, and the virtual protect X. And as I've mentioned, these API calls are existing in a functions directory in Nimjector. So you can just check these functions and the same API call. So you can check here. There's a .nim file after copy pasting and tabbing, and you can see the definitions of this API call. So what the tool does is it just compiles the contents of each code snippet into one. So as you can see here, the contents of this are just being written into this one, which makes it a framework, modular framework. And as I showed you here again, in the models that the techniques are being written here, and if you want to check the early bird technique, it uses a create process, which is being used here, and virtual alloc X, write process memory, and queuser APC. So with this demo, you can see that the framework being built heavily relies on how you define it, on the configurations, as well as how you write it in a modular one. Since if you have a create process or virtual alloc X code snippet, if you have different techniques that are using virtual, let's try to check how many techniques those use virtual alloc X. So cat grep virtual alloc X. So we can see here that there are 4 techniques that are using virtual alloc X, which means that with our modular framework, we can easily reuse the code that we have defined and make the other tools use the virtual alloc X that we have defined, and yeah, it should work moving forward. But still, we should account that the custom arguments that are being used in different techniques. If you're familiar with the technique that it uses a different argument, then you should define it in the customs. I'll give a different example. Let's use this early bird ABCQ virtual alloc X. You can see here that you can define here that the custom arguments of the API call is being used without relying on the functions directory. So now let's try to compile a binary and see if it can detect something. So let's try blue def f. Let's use samples. No, samples. Malware samples. So there are malware samples here, and let's try to check this. So you can see here that nothing is detected, so let's try another one. Well, let's just try the existing one. So you can see here in the sample that the potential injection technique was able to, the tool was able to detect vanilla technique with 87% chance because it was able to detect virtual alloc, create thread, and wait for a single object. And with that static checks, it was able to somehow give you an idea what API calls was being used on that binary that you want to test and the definition of each API call that was being used. So, with that, any questions? Any questions? If someone asks me a question, you can get a free TS t-shirt on that booth.
Uy, I asked you a question I didn't get a shirt.
Sir, what? Anong question, sir? No, any questions about the talk? So anyone would want to ask a question? Sino? Wala. Ay, si Papa J yung crush ko sa root code. Sino? Wala. Si Papa J. Any questions? If none, please feel free to hit me up during this con or just on LinkedIn if you're interested in red teaming, since I'm a real red team enthusiast and I would love to see some people who pursue red team, especially malware development. So if you would also want to contribute on the tool, just feel free to check the tool itself on GitHub and feel free to approach me so that we can talk about the capabilities and future development plans of this tool. So lastly, I would like to highlight some people who helped me on formulating the idea and validating that my idea is good for this talk. So first is Redactor, Mamaristi, Seymour, Ian Secretario, and Jigglypuff. Thanks to these guys who helped me building this tool. And lastly, again, I'm Ariz and I'm from TIO Cyber Solutions, and thank you for attending my talk.